All right, let's get this practice test done for Unit 14 so we can get a good score on the test and show what we know how to do. Remember the instructions here, show all your work in thinking, round to the nearest hundredth. So remember, we're going to round to 2 decimal places when we need to. And let's start off with number 1. It says make a proper scatter plot for the trip data cost. And we've got the number of people and we've got the cost of the trip. This is usually going to be the independent variable, the x variable, that will come first. And then second is going to be the dependent variable, so that's going to be y in this case. So I'm going to write down cost of trip here, and I'm going to write a $sign there. And then over here we're going to put number of people. So we've got this labeled, but now we need to figure out how we're going to scale this. So we need to fit on the x-axis. We need to fit from at least 2 up to 8. So maybe we'll go by, just count by 1 and label every 2. So this would be 2, and this would be 4, and this would be 6, 8, 10, and 12. We don't have any data that goes up that far. And then let's see here, we need to fit from 700 up to 2,500. So 2,500 is the biggest, so that's what we're going to need to consider here. So we've got 5 tick marks here. So let's say that this is 500, then 1,000. And what that will allow us to do is that will allow us to get up to 2,500 here. So I'll have to squeeze that in right there. Probably should have scaled that first. All right, so we need to make the scatter plot. So we've got it scaled and labeled now. We're going to put the points on there. So we're going to do 2 and 700. So we're going to put a point about right there. Then 4 and 1,300. So 1,300 somewhere right around there. 6 and 1,900. 1,900 is just shy of that 2,000, so we'll be about right there. And then 8 and 2,500. 8 and 2,500, so we're right in there. So that's what that looks like, and it says, what is the equation for the line of best fit? Well, we could do the old school method of kind of picking one on the high end and one on the low end, but we can use the calculator on this one. So let's go ahead and pull up the calculator. I'm going to grab the TI-83. I've already put the data in here just to save us a little bit of time. So I'm going to go ahead and take a look at the lists. So we'll hit Stat, and then we'll click Edit. So I've already taken the time to put that in there. Always a good idea to double check and make sure that you've put the data in there the right way. If you put in the wrong data, you're going to get the wrong answer. It gets really frustrating. So I'm going to hit second quit. I'm going to come back here. I'm going to hit Stat and Calculate. We want to calculate a linear regression, and I'm on an 83, but it works basically the same way for an 84. Now, the calculator assumes that we're doing L1 and L2 unless we've changed it. So that's what this is going to do. We're going to hit enter, and there we go. So we get, remember, it's y equals ax plus b rather than mx plus b. So we get 300 for the slope and 100 for the y-intercept. So I'll come back over here, and I'm going to write down y equals 300x plus 100. So there's the equation, and it says what's the correlation coefficient. So let's go back here. Now remember, unless we turn the diagnostics on, if we reset the calculator or something like that, it's not going to give us the correlation coefficient automatically. So what I'm going to do is I'm going to grab the catalog. So I'm going to hit second and catalog. The letter is already highlighted right here. So all I need to do is I need to find the D's. The D's are right here above the x to the -1 key. So I'm going to hit that and then just arrow down until we find the diagnostics on. We can turn them on or off. They're off right now. We want to turn them on. So we're going to hit enter. Now I'm just going to recall that last command. That was a linear regression. So I'm going to go ahead and hit enter. There it is. Now notice that we've got the same slope 300, the same y-intercept of 100, and then we've got the r value right here. Now this almost never happens, but on this particular one we get r equals 1. Okay, so that means that is a ridiculously strong positive relationship. In fact, that's a perfect relationship. This almost never happens. Now it's kind of to be expected on a problem like this where they're charging for the number of people that go on the trip. So not too bad here. So let's talk about how we interpret the two of these. So let's talk about the slope. So if we're talking about slope, the slope is 300 right here. So the slope is $300 per one person. Okay, so there's our slope right there. Now if you wanted to write it out and write down $300 per person, that would be okay. Totally okay with that. And then let's talk about the y-intercept. So on the y-intercept is 100. So $100 is the cost of the trip, with no people. Now, there are times when we're doing something like this and the mathematical model makes perfect sense, and then other times it kind of breaks down and it's not very logical. Now, if nobody's going, then clearly we wouldn't pay any money for it. But this is kind of, maybe you could think of it as a setup cost, maybe a traveler agent fee or something like that. So it costs $100, but then once we pay that fee, we can add as many people as we want, and it only costs $100 per person. Okay, let's take a look at the next part of this. So down here it talks about use the line of best fit to predict the cost of the trip for 30 people. What concerns might you have about this prediction? So if we're talking 30 people, the number of people is X. So what this says is X is equal to 30, and we want to know what is Y, what's the cost of the trip, like it says up here. So let's just go ahead and write down the equation. The equation would be Y equals 300 times 30, and then plus 100. So we're going to do the multiplication right here. This ends up being 9,000 plus 100. So it ends up being $9,100. Okay, so $9,100 for that many people. Now, do you have any concerns about this? So one thing is, the data that we have here is it only goes from 2 to 8 people. So this is what we call way outside the scope of our model. Now, we'll assume that it's right for now, but maybe one concern is, can we really have that many people going? So can we really have that many people? All right, so this would be outside of our model, and maybe we run into something like, hey, the bus doesn't hold that many people, or there's some things where we have a van excursion, and that wouldn't work, or maybe hotels or something like that. So that might be one of our concerns, but we're going to go with this prediction right here. And then it says use the line of best fit to predict how many people could travel for $5,000. So let's go ahead and use our model here. So what they're telling us on this one is that Y is equal to 500, because they're giving us a dollar amount over here. Sorry, 5,000. So we're going to do 5,000 equals 300x plus 100. I'm kind of thinking ahead here. So we're going to go ahead and subtract 100 from both sides. That's going to be 4,900 equals 300x. And then we'll divide by 300, and then we'll just throw that in the calculator and see what we end up with. So on the calculator, we're going to do, let's see, I'll clear this off. We're going to do 4,900 divided by 300, or I suppose we could have just done 49 divided by 3. That would have worked out just fine. So that would be 16.3. So 16.3, we'll do 3 people, we'll label that, okay? Now, not very realistic that we could have a third of a person, so we'd probably say that we could definitely afford to have 16 people go. So I'm just going to put approximately 16 people. That'll be kind of like a real-world interpretation of that. Okay, let's come down here and we'll take a look at the next one. This graph and table, they show the 400-meter individual medley swimming event in the Olympics from 1964 to 2008. Now, this is listed as the years after 1964. So the year 0 would be 1964, and then 4 years later would be 68. And then, 68, make it look right. Okay, and then this would be 72 and so forth. So these are all the Olympic years. Now you can see that there's clearly some sort of association, some sort of correlation with this. We want to put this data in the calculator, and we want to figure out what we've got here. So I'm going to pull up the calculator here, and then I'm going to shrink this down so we can see both of them at the same time. Now you'll notice that I've got a whole bunch of data in here. I kind of did this ahead of time so we could be all ready for this. So you'll notice that I've got year 0, and then I've got the 285.4, and this is seconds, so it'd be, what do we got there, a little bit more than 4 minutes or so. And then the times continue to go down. Now, I did double check and make sure that all of these were in there the right way. And we won't worry about L3 and L4 here for just a second. So it says find a linear regression model on your calculator. So I'm going to hit second quit. And again, we're on the 84 now, so it's going to look slightly different, but a lot of the stuff is very much the same. So I'm going to go to calculate. I'm going to do number 4. And again, this tells us what lists we want to use. So I'm going to make this an L1 for the X list and L2 for the Y list. Again, I'm hitting second and 1 and second and 2 because of these blue letters up here that say L1 and L2. We don't worry about the frequency or the store the regression equation. We're going to hit calculate, and this is what we end up with right here. So we end up with a slope of negative 0.903. So that 3 is not enough to bump this up, so we're going to call that 0.90, negative 0.90. and this is 281.326. That 6 is enough to bump that up. So here's what we're going to write down on this. So we're going to do y equals, this is going to be negative 0.90x, and then we're going to put plus 281.33. Now make sure you're careful with the rounding on there and everything. Now again, I don't have the diagnostics set up on this one, so I'll go ahead and turn those on and we'll check that again really quickly. So I'm going to hit second and catalog. I'm going to hit the D, come down here, and we're going to hit the diagnostics on and hit enter, so it actually performs that. I'm going to hit second recall a couple of times so we can, so notice that this calculator, it'll tell you that you're actually using L1 and L2. So I don't know if you caught that, but it actually does show this command on the screen when you hit that from the calculate menu. So I'll just hit this. We get the same answers for the slope and for the y-intercept, and we get negative 0.930. Again, always look at that third decimal place so we can figure out where to round this. So this is going to be negative 0.93. So r is equal to negative 0.93. Now, what does this correlation coefficient tell you about the linear regression model? Well, the sign tells us that there's a negative relationship. Okay, so it would have a negative slope. So negative slope. It's going to be going down from left to right. And the fact that it's a number that's pretty close to 1 or negative 1, we would say that there is a strong relationship. Strong relationship. Okay? Now, what do the slope and the y-intercept represent in this particular case? Well, in this case, remember, this is going to be, for the slope, we've got negative 0.90. That's going to be a y value. That's in seconds. And then the denominator, that's going to be in years. Okay? So what this means is they're actually taking off almost a second, a little bit less than a second per year. So we're going to draw a little arrow here. We're going to say time is decreasing. Heard some people use some really good words like that. Time is decreasing by, we'll say, about 1 second every year. Okay, so it's going down by 1 second every year. And it says, what does the y-intercept represent? Well, the y-intercept represents, so this is the slope, I'll put that. And then we'll have y-intercept. That's going to be 281.33. And we're going to say something like this. We're going to say that this is the, so we'll say is the approximate, and we'll say estimate of time in 1964. Okay, we'll say the initial time or time at beginning. So time at beginning. Like when they started the stopwatch on this particular one, it was 1964, so that's why we've got that right there. Now, we can actually come over here and we can take a look at this. In 1964, it says it was actually 285. So again, this is where a mathematical model doesn't get everything perfect, but again, if we were to draw this right here, so 281, I mean, it would look something like, maybe something about like this. Again, we're looking for the overall trend. We're looking for a rough estimate of what's going on. That's what happens when we do a regression, is we're taking the points, we're trying to figure out what's the best equation that would represent that pattern there. Okay, now it says the last part on this side, it says use the equation to predict the time at the 2020 Olympics. Well, the 2020 Olympics, let's see, we'd have to take 2020, and we'd have to subtract 1964 to figure out how many years that is. 1964. Don't know why I'm writing that way this time. So that's going to be about 56 years. Now, the fact that this is years, that tells us that x is going to be 56. So we're going to put 56 into our model. So this is going to be y equals, so here's our model right here. They're going to lose about a second, a little bit less than a second for every one of those 56 years. And then we're going to add that initial starting time, or that initial estimate for what it would be. And that is 281.33. I got to get that right, 281.33. And then we're going to throw that in the calculator. So let me see what we get when we pull this up here. Again, I'll just hit second quit. I'll clear the screen off. And then we're going to type in here. Let's see what we've got. We're going to type in negative 0.90 times 56. and then we're going to add 281.33. So we'll hit enter. We got 230.93. So this is 230.93. Now, it would be really good if we put a label on that. So let's make sure that we get this right. The label on that, because that's a Y value, that's going to have to be, we put in the years, this should be seconds. Okay. So in 2020, we're predicting that it's going to take about 230 seconds, so less than 4 minutes. We go from well over 4 minutes in the 60s to well under 4 minutes in 2020. So I guess we'll see how that goes. All right, let's take a look at the next page. Okay, let's go ahead and take a look at what we've got going here. On the back side, we've got a table that shows the population since the year 1900. So this would be 1910, 1920, 1930, and so forth. 92 million people in the United States in 1910, and then it just continues to go up from there. So let me pull up the calculator, and you may have noticed before, if I hit edit and we take a look at this, I actually put this data in here and made sure that I had that all right. Now we've got two options at this point. One thing we could do is we could just say, hey, we're going to use L3 and L4 on all our calculations and then change those. The other thing that we could do is we could come over here and we could actually store them in L1. So I could do that thing where we do, we just hit, let's see, it would be L3, and then it would put L3 in L1, and then we're all set to go. Now, I'm inclined to do that because we tend to make fewer mistakes if we're doing kind of the same thing every time. So I'm going to go ahead and hit L3 and L1. I'm going to come here and I'm going to do, let's see, second and a 4. That'll give me L2 is equal to L4. So now I've got a repeat of each one of these, and just for the heck of it, I'm going to clear these off just to make things look a little bit better here. So I'll hit clear, and then we're all set to go. So I know I've got the accurate data in here, and maybe while I was doing that, you went ahead and typed it in. Again, we want to make sure that we've got the right data in there every single time, because if we don't, we're going to make mistakes. So I'm going to hit second quit. I'm going to clear everything off here. I'm going to hit stat, and we want to calculate something. We want to calculate a linear regression. So I'm going to hit number 4. Again, by default, it will be L1 and L2. Wouldn't have been a big deal if we had done L3 and L4. We're going to come down here, and we're going to calculate. Now remember, we've got the diagnostics on, so everything that we need is right here, but we just want to make sure that we've got this right because this one has some rounding challenges on it. On this one right here, so it's 2.00 for the slope, but that's a 5 right there, so that means we're going to bump this up one. So this is going to be 2.01. So I'm going to shrink this down just a tad so we can see the calculator and the paper at the same time. So I'm going to write down y equals, so this is going to be 2.01x, and then plus, we'll round this one to 2 decimal places, so this is 0.638. So this 8's enough to bump that up, so it's going to be 62.64. So 62.64. So there's our answer on that. The R value, and what does it tell us about the linear model? We'll take a look at this. So R on this one, the correlation coefficient is 0.99, okay? So what that means is this is a very strong positive relationship. Okay, very strong positive relationship between time going by and then the population of the United States going up. So the next part it says use the equation to predict the U.S. population in 2020. Now 2020, if we wanted to write all of this down here, this would be subtract 1900. So this is going to be 120 years. We can kind of keep track of that just right here. So we're going to put the number of years as 120. So that's x is 120. Okay, because that's what we've got represented right there. So we're going to write y equals, this is going to be 2.01 times 120 plus 62.64. 62.64. So we'll throw that in the calculator. So we're going to do 2.01. And then I'll put this one in parentheses, 120, and then we're going to add the 64.64. So we'll go ahead and hit enter, and we get 303.84. So we get 303.84, and that would be in millions of people. 303.84 million people. So I'm going to go ahead and circle this, but let's make sense of that. Remember, this would be in millions of people. So this is going to be 303. I'm just going to write this off to the side here. And then 84, we've got that one. And then this would be the thousands. So this is millions. This is the thousands. So it would look something like that. That would be the number that we're looking at. So 303 and a little bit more million people. Now it says use your calculator to help you create a residual plot. And then it says, what does the residual plot tell you about the linear model? So I'm going to come back here. I'm going to go on the calculator. We're going to take a look at this. And remember, if we hit second and list, remember it has the residuals right here. Okay, so we're in good shape there. It stores that automatically every time. Now here's what I'm going to do. I'm going to go back to our list. And I'm going to edit this. Now, you don't have to do this, but if you wanted to, we could put the residual list in L3. So I'm going to go ahead and hit second and list. I'm going to hit number 7. So what it's saying is make L3 the residual list, and we're going to hit enter. So there it's keeping track of the residuals. So we're in good shape there. Now I'm going to come back over here, and we're going to make a scatter plot, and we're going to talk about a couple different ways that we can do this. So I'm going to hit second and y equals. We'll do a scatter plot. I'm going to go ahead and turn this on. Number 1 is the scatter plot. Now remember what happens with this. We use the same X list as we do if we were to make a scatter plot of this data right here with years and the population in millions. We do L1 and L2. So this would be the X and this would be the Y. We want to do the residuals. So there's a couple things that we could do. We could change this to L3, which would be pretty easy. Or, I mean, that's the easiest thing to do. We can just do it right here. Or we can do this. We can hit second and list, and then we come down here and hit 7. So we're using the same X list, but now we're using the residuals. Okay, now a quick way to get started on this is to just have the calculator figure out what a good statistical window would be. So we can hit zoom, and then again, I think you remember it's zoom 9. Zoom 9 is zoom stats. So I'm going to go ahead and hit enter, and this is what it looks like. Now that's not too bad, looks okay to me. Let's see what it did window-wise. So window, it went from 2 to 98. So the X that we have, the smallest is 10, and the biggest one we have is 90. So let's maybe adjust this a little bit. Let's just go from 0 to 100. Okay, so it looks pretty good. And we'll put a tick mark every 10. And then it shows these guys right here. Let's clean this up just a little bit. Let's say we go from negative 15. Let's make some nice numbers here, to positive 15, and we'll put a tick mark every 1 unit. That'll be okay. Now that looks pretty good. Let's see here. Let me go back to the window here. Oh, the scale. I didn't change the scale. I should have done 10. Okay, there we go. That looks a little bit better. Okay, now we can go through, and it says use your calculator to help create a residual plot. Let's just go through here and let's hit trace. The very first one is 10, so that would be right here, the first tick mark, and then positive 9.3. Well, remember, we said from negative, let's see, we went from negative 15 to 15. So I'm going to put negative, let's see, this would be 3. If we went by threes, this could be negative 15, and this could be positive 15. So I'm going to put a 3, a 6, a 9, a 12, and a 15. And this would be negative 3, negative 6, negative 9, and negative 12. Okay, that'll look pretty good there. And I'm going to zoom in on this just a little bit. That'll probably make it easier for me to write my answers on this. Okay, so we're going to slide over here. So let's see, the first one is 10 and 9.3. So again, this is 10. I'm just going to label 20, 40, 60, 80, and then 100. So we don't have to label every single one of those. So this is going to be, let's see, 10 and 9.3. So about right here. The next one, 20 and 3.2. So about right there, just a little bit more than 3. That's a nice convenient way to scale that. Okay, this one is 30, and gosh, it's almost 0. It's almost right on the line right there. It is just barely positive, so we'll put it just barely above the line like that. The next one is 40 and negative 10, so that's going to be about right here. And then the next one is, let's see, 50 and almost negative 11, so let's see, maybe a little bit lower. Okay, so about like that. And then 60 and negative 2.93, so that's about 3. So we're looking about right there. 70 and positive, so now we're at about positive 2, so we're a little bit above the axis right here. 80 and 3.96, so that's about 4. So somewhere around right there. And then the very last one is going to be at 90 and 5.9, so about 6. So 90 and 6 would be about right here. Now, what we're looking for here, remember, it talks about what does this tell us about the model. So let me go ahead and go full screen on this and snap this back to width here. We've created the residual plot, so you can just see the answer right over there. And it says, what does the residual plot tell us about this linear model? Well, because there's this pattern of above, then below, and then above, this data is not very well fit by a line. So linear model is probably not the best. Now, that's the tool that we've got right now. That's what we focus on most of the time. We may be able to do something that's a little bit more sophisticated, but all we want to be aware of is, yeah, it's probably a decent model, because notice again that correlation coefficient. It's 0.99, so it's pretty good at predicting this, but there's something else going on here. There's something going on behind the scenes. Okay, let's go ahead and take a look at the bottom here. For the next couple of problems, it says for each relationship, determine if you believe there would be a positive, negative, or no correlation. Then decide if the causation statement is true or false. So on this one, it says the relationship is time spent studying and test scores. All right, so let's think about that for just a second. Let's maybe just draw a quick graph that may be helpful. So I'm going to put time right here, and then I'm going to put score right here. Well, if we don't study very much, we're probably going to get a low score. And if we study a lot, we're probably going to get a high score, and then everything in between. Again, this isn't a perfect prediction, but I'd probably say that this is a positive relationship because they both do the same thing together. So as time gets bigger, scores get bigger. As time gets smaller, the scores would get smaller. And then it says, therefore, the more you study, the higher your test score. So is that an actual causation thing? I'd probably say that that one is true. That's probably true. Now, the next one says high temperature and football. So high temperature meaning the daily high temperature. So I'm actually going to write that in there. So the daily high temperature and football attendance. Well, let's think about this for just a second. So if we put temperature right here, and then we put attendance right here, let's think about this in the fall. So as the temperature goes down, a lot of people go to football games in the fall. So in the fall, the temperature is going down, but the attendance is going up. So when the temperatures are fairly low, we've got a lot of people attending. And then as it gets warm in the summer and stuff like that, there aren't many football games and things like that. So this would be a negative relationship. So a negative relationship. And it says low temperatures cause more people to attend football games. Well, we'd probably say that that is a false causal statement because it's not the temperatures that actually cause that. It's just the fact that they both coincide. It gets cooler in the fall, and that's when football season is, and that's when people attend more games. Okay, number 19, it says the amount of exercise and the amount of heart disease. Well, gosh, if you exercise a lot, so if you do exercise a lot, you're probably going to have a low amount of heart disease. And if you don't exercise very much, you might have a lot. Okay, so this one is also negative. Okay, and it says your level of exercise determines your amount of heart disease. Well, let's see. This one could be maybe either. Okay. So I'm going to put true or false on this one. Again, when we're trying to make these judgments about the causal relationship, whether it's correlation or causation, on that one, it's a little tougher to tell. There may be some genetic things and stuff like that behind the scenes. So that one's a little bit tough. So just be aware of that. Now, on the last couple, all we want to do here is it says look at the information given and then determine if there is a positive, negative, or no correlation, and then decide if it's just correlation or probable causation. Okay, if there's a causal relationship on this one. So this one right here, again, you don't even have to look at the labels here. This one's going down from left to right, so this one's going to be negative. Okay, this one's going up from left to right, so this one's going to be positive. Okay, and this one's just kind of a blob all over the place. If we were to draw a line, it would basically be flat, so we would say no correlation. And remember what that means is the slope of the line that would go through there would be roughly 0. Now let's look at the actual information here. It says the number of absences and the final class grade. Well, gosh, if you're not attending a lot, so if you're missing a lot of class, you're going to get a lower grade. So we would say this is probably causation. Causation. Okay, and then this one right here, the age of the car and the stopping distance. Let's see. I mean, hopefully we're keeping things in tune with the car and changing the brakes every so often, we would maybe say that that is a correlation. So I'm going to say correlation. Now, you could make an argument for either one of these, but this would be my argument for this being just a correlation. As things have gotten better, technology-wise, with cars and engineering and design and stuff like that, it may be that the older cars just were not designed to stop very well. It may have something to do with weight or different things like that. So we could probably get away with either. In fact, I'm going to put in parentheses that on that one, maybe we take either correlation or causation. And then this one right here, we just flat out say none. There's no relationship there, so we really don't have anything to say about that. Now, this last part, I'm going to leave this blank. It says, what was the U.S. population in 2020? What I'd like you to do is I'd like you to look that up and then figure out how close we actually were in number 14, and then maybe try and find an exponential model and use that to predict and see if that's any better. We knew that because of the residual plot, there was something else going on there. So maybe do that as a little challenge one and see how that works out. All right, good luck on the test.